Okay, let's continue on the generator modeling session. Okay, we quickly go through what we learned from last week. So our goal is to find a matrix which can tell how the flux can change with current. For round rotor generator, we have some rotor winding, have stator winding, and for ceiling pole rotor generator, we also have rotor and stator windings. Does anyone remember how many windings do we have for round rotor generators? As a minimal number of windings we have to consider for round rotor generators.
Wasn't it? You have to add another coil, so it'd be 4.
Yeah, it will be. What will be the total number of windings? 4 plus 3. We have to have 3 stator windings and 4 rotor windings. For ceiling pole rotor generator, we have 3 plus 3. We have 6 windings. Any question? Okay. So and we use ceiling pole rotor generators as examples. So we have 6 windings. So which means the flux linkage vectors can be represented by this vector with 6 elements from side A, side B, side D, side C, and capital F, capital D, and capital Q. So capital letters indicate rotor windings, and lowercase letters indicate stator winding. Similarly, we have also the vector on the current. And the reason why the first 3 elements of current, IA, IB, IC, they have a negative sign because I explained for the stator winding, and so those current will induce the voltage to power the load of the system. So their current will be opposite to the direction of a flux linkage. But on the rotor winding, so those winding will be the load of in each winding. So their current will be in the same direction as flux linkages. Okay, so in order to figure out the values for the parameters, each parameter in this matrix, which represent inductances between any 2 windings, mutual self-inductances, we need to consider this simple that simple figure with a revolving magnetic field between 2 windings. Okay. So the inductance is proportional to the product of the number of turns of 2 windings and also the permeance. Permeance really depend on the air gap. So if the air gap between the 2 windings is increased, so the permeance will decrease. So permeance is like a magnetic conductance of, if you compare to the electric conductance of electric circuit. Okay, so so there are different combinations in that inductance matrix. Some inductances are self-inductances, which means the 2 windings actually are the same winding. So you can just get rid of 1 winding in that figure. Some inductances are the mutual inductances, the 2 windings are different. And also, for some cases, the 2 windings are stationary. For example, for the stator windings, they don't move; they just face there. But the magnetic field is revolving, which is with the rotor. But for some mutual inductances, so 1 winding is in the stator, 1 winding is in the rotor. So the one on the rotor will be revolving together with the magnetic field. Okay, so for different combinations, so we have discussed the functions for the inductance changing with time or changing with the angle of this rotor theta. Right. So if the 2 windings are both from a stator, such as anything in this block, so the product of 2 ends, Ns and Ny, will be constant, but the permeance will be changing periodically. with a period of 180 degree. Every 180 degree, the permeance will reach the maximum value. Okay, so if we want to use the function of theta to model the green block, so it will be a periodic function with a period of 180 degree. So if you use cosine function, so you're going to see cosine 2 theta plus certain phase. So this is what we derive. And definitely the L0 just indicate a constant term. So there's a maybe component which contribute to the flux linkage that doesn't depend on the position of the rotor, which is like net loss of a flux linkage from the inside of the generator to the air due to the air gap. The next one will be the element in those two blocks. Because the matrix is symmetric, so you only need to study one of the blocks. For those, anyone in that block, one winding is from rotor, one winding is from stator. So which is like the rotor winding will be carried by this magnetic and revolving together, right? And you can assume the stator winding is evenly distributed along the entire air, so entire space. So the air gap will be constant. So if you can design this generator very well, so this winding is evenly distributed along this entire stator, inside of the stator. And this one is revolving together with the magnetic, okay? So which means the permeance will be basically constant, but this product will be changing periodically. Because right now, the two axes of the two winding in parallel, that is the largest value if we consider this as a dot product. But if they turn by 90 degrees, this one will become 0, right? Okay, so if it turn by 180 degrees, that will be pointing to different directions. So product will become -1. So for anything here in those two blocks, and they will also be periodic function with cycle of 360 degrees. So if we want to use the equation to represent their changing will be something like this one, will be a cosine function. The beta just indicates some phase, depending on which winding you're talking about. Okay, finally, anything here, which is like both windings are carried by the magnetic. So no matter how this one revolve, their coupling always constant and the permeance always constant. So that everything here will be constant. Okay, so the next following slide, just figure out the phase for alpha and beta. So we have finished those slides. We just use phase A as one example to indicate for the self inductances LA, LBB, and LCC. So when that angle is 0, which is exactly same at what is showing on this slides. So and this when the axis of magnetic field is same as axis of the windings, which means theta is 0, that it will be the largest value. So which means for LA, LBB, and LCC, so this alpha is 0. Oh, sorry, this alpha is 0 for LA, and LBB will be adding, you have to add 120 degree. LCC you have add 240 degree or negative 120 degree. Okay, so LEB, we figure out when those are the three axes of the three windings, and when the rotor direction is lagging the phase A by 30 degrees. So when you couple the winding B and A, you can maximally utilize this magnetic this rotor. So that will have the overall smallest air gap between A and B. So negative 30 degree or positive 150 degree will give you the maximal for this case will be maximal permeance. Then a stator rotor mutual inductance is simple. We just basically just phase is 0, so that will be the largest one. Okay, so that is same for anything like LAF or LAD, because capital F and capital D, the field windings and the damper winding in DS is both in the same direction. So they have exactly same form of the equation, but the magnitude can be different. Quinter's book explained the estimation of those two values, but I won't go into the details. But those can be estimated by study, right? Which can be part of the parameters of the generator model. And in the Q axis, which will be lagging this one by 90 degrees, so it's equivalent to change this one to a sine function with negative sign. If you define Q axis to be lagging D axis by 90 degrees, so this negative sign should be removed. So that will become positive. Okay, so this figure just show all the waveforms, all the curves of the cell of mutual inductances involving a stator or one or two stator winding and one rotor winding. So first one is something like a LAA, LBB, LCC. So each of them will be positive because the self inductance between the same one is always positive, but it will be periodically changing around some value, which is this constant value at a certain magnitude. They just have 120-degree phase displacement. And the second column is the stator mutual inductances involved, maybe LAB, LBC, LCA. So they are all negative. Because phase A and phase B are separated by more than 90 degrees. Okay, so if you project to any coordinate, they will be opposite. They have they're pointing to different direction. So which means their mutual inductance will have negative effect. So will be changing around some negative value. So you notice this has a period of pi, right? This is also have one period of pi. And the last column will be the stator to rotor mutual inductances involved. The first letter is from ABC, the second letter from F, capital D, and capital Q. So those basically just sine and cosine function. So they will have center value 0. They just periodically change with a cycle of 360 degrees. So one period will be 360 degrees or 2 pi. Okay. Any question for this slide? All right. So those three columns of curves are representing how the inductances change for ceiling pole rotor generator. But if you try do the same approach for a round rotor generator, are they same or different? Any thought? Air gap is same for what do you mean? Just
for cylinder generator, the air gap is always changing.
yeah. For round rotor generator, the air gap is same. Yeah. Okay, so anything caused by change of air gap, which means change of the permeance, that variation will disappear. For instance, those two, right? Those two are caused by changing permeance or changing the air gap. So those two will be constant. So for round rotor generator, this curve will be just straight line. Okay, this part is 0. Definitely, you have to assume this round rotor generator is perfectly designed, right? But in reality, there may be a little variation. But you can just assume this one to be straight line, this straight line, and those three are negative straight line. But how about this column? So for this case, permeance is a constant. But the coupling between the two windings, one on the stator, one on the rotor, that coupling still change, right, periodically by 360 degrees. So those on chain, they'll be same even for round rotor generator. Okay, so that's why there's some some research. They just use round rotor generators, even it has one additional winding, but they make a lot of things easier. So at least those inductances will be almost constant. Only those three will be theta dependent. Okay, last we haven't talked about the bottom right block of the indulgent matrix, so which will involve those elements. Both subscripts come from F, D, Q. Okay, so those are all the combinations. So the conclusion is those are all constant. Okay, because both 1D is on the rotor, and when you revolve together with rotor and say inside of stator, everywhere same, every direction same. So there's no reason to change if you design this generator well. Okay, so it simply does all constant. Okay, and we just make it simple. We just call we use a lowercase l just indicate this could be a time invariant function, but now you call it a capital L F, capital L D, capital F Q, because those are just self indulgences with rotor. Okay, then there are also mutual indulgences, which are on the off-diagonal elements on the last block, such as LFD, LDF. Because it's mutual, we just use the letter M. We just call it MR, which means mutual indulgence in the rotor. And this is also mutual indulgence, but because field 1D and damper 1D in Q axis, they are pointing to a different direction. So which means the inner product of two number of turns will be always 0. So this one always 0. That is also always 0 because the two 1D are orthogonal to each other. Okay, so finally for that gray block, that will be very simple. So the diagonal element will be constant, and off diagonal element only just have one, which is not 0. Okay, to summarize, those are all we have derived so far for the flux linkage equation. So the indulgence matrix will have diagonal block. The first diagonal block is this one. The second will be this one, and the off diagonal block will be this one. This is symmetric. So you can just do the transpose. So this one will give you the other one. So let's do some further thinking based on those formulas. Okay. So in last lecture, I said this is our first model for this unit generator, but it is not good model. Why? Do you remember why I said it's not good model?
Was too much parameters.
Not because of the number of parameter, because of now the parameter are constant, right? So you can treat each indulgence, mutual self-indulgences as parameter, but most of them actually theta dependent, depending on the position of rotor. And when you use this model and you don't know the actual position of rotor, you actually don't know the true value, okay? So each value will be periodically changing with theta, but you don't know what their value is. So it's not a good model. A good model means first, all the parameters have to be constant. Because the constant, when you test this machine at this location under this condition, you can pass the parameter to somebody else. They will just, it's safe to use the same set of numbers for other study, right? You don't want, when you disconnect the generator, everything change. You just shift to some other value. All the modeling work will be useless. Second, we definitely need to have the smallest set of parameter, which means if your model has 1,000 parameter, my model has 100 parameter, we can generate exactly the same result. My model is definitely better, more efficient. So we need to figure out the smallest number of parameter which are enough to do the study without sacrificing any accuracy. So definitely this model doesn't meet the first expectation. So in this matrix, only this block is constant and the other 3 blocks all theta dependent. So then we need to think about why what make this block be constant, but the others not, because this block is estimated in the reference frame which is revolving together with the rotor, right? The others all involve some stator frame. So that make the LSS or LSR theta dependent. Because theta is time dependent, so those are also time dependent. Because they involve at least one winding which is from stator. Okay, and we can pick the second equation from here, which is the psi FDQ equals LRS multiplied by this one plus LR multiplied by IFDQ, which will be this equation. So I intentionally highlight this item because only that one is theta dependent. Anything else, everything else will be constant. Because this is if you spell the psi vector, which will be psi f, psi d, psi q, there's no theta. This current has IA, IBIC, no theta. And here's no theta, here's no theta. Only this one has theta. Okay. So this one gave us some idea on how we can get rid of theta in our next model. So we move this item, a theta dependent term, to the left side of the equation and everything else to the right-hand side of the equation. And the right-hand side doesn't depend on theta at all, at least not explicitly depending on theta. Okay. So which means the left-hand side essentially doesn't depend on theta. Although it has maybe item which is theta dependent, but we can make it be theta independent. So for instance, maybe we can introduce some transformation. The transformation is theta dependent, but this theta dependency will cancel the theta dependency with this LRS. Then we need to figure out, so at least the right-hand side of the equation prove this one is doable, it's completely feasible, right? So we just need to figure out what transformation we can utilize to cancel the explicit dependence of theta. So if we can do that, we can just transform the current as I prime, which is some current, but still carry all the information of I. And also we can call the L matrix transformed by P inverse as some new L matrix. So we are going to utilize this one as the parameters for the coupling between the stator and rotor winding. Any question? Okay, so this is our starting point, LRS, right? Every item is theta dependent. So how can we get rid of the theta dependency? And we know this item is when we do calculate the product of LRS and the current vector of the stator current vector, this one essentially is theta independent which should be equal to the right-hand side. So our goal is to find out how we can transform to this item, both are not theta dependent. Okay, that's one thing we can do. We just simply finish this matrix multiplication. We just calculate the first matrix is just diagonal matrix. It just vary the value of each row. So we just keep that there. We calculate the product of the next two. So we'll have those three elements become a vector. Okay, by coloring those vectors differently, actually this vector of three elements only show two different elements. Those two are identical. And this is another one different. Okay, so how about we just define each of those, the first two as ID. Let's just call it some current. We just get rid of the theta dependency. The second one is different. We just call it IQ. That's done. Okay. Right. So those ID IQ will be part of this I prime. And we just forget those theta dependent formula. We just start using the ID and IQ. But definitely we need to figure out a way to transform back to IAB. Your IAB represents actual current in the network. If you measure the current in the phase A, phase B, phase C, those are the real current. But this ID IQ, we just define this expression as ID. We just don't like to see theta. That's it. We haven't figured out what transformation we can use. But let's just continue. Okay. To make things simpler, we just consider balanced steady-state condition. So balanced steady-state condition, if we call the IA is proportional to some sign function with 0 phase, IB will be the same function with negative 120 degree. IC will be the waveform added a positive 120 degree. Okay, and for the steady-state condition, we know the theta, which is on the position of the rotor. We have this formula, which is equal to the omega r, which is the rotor speed times t plus the delta. Delta is actually the rotor angle. The QS is relative to a synchronous frame. Okay, that synchronous frame is revolving at omega s. Omega s is actually the common frequency of the system. This negative half pi just indicates this is about QS, it's not about DS's. Okay, and for steady-state condition, the omega r is same as omega s. There's really no difference about omega r, omega s. Omega s doesn't represent the true location of rotor. It just represents there's a common reference, which is like 60 hertz. But omega r, it can carry the real-time variation of the rotor. Okay, but for steady-state condition, they're basically the same. So next, we want to calculate ID and IQ. Okay, in order to do that, we have to plug in those IA, IBIC into those formulas. Here we have to utilize this this formula of sine cosine function. So when we calculate the product of one sine function and one cosine function, so that will be equal to half of the sine of angle, the sum of the angle and the difference of angle. Okay, so this is the first item. And if we shape the product, each angle by 120 degree, we definitely have the second, the third and the fourth term. And we further shaped by another 120 degree, we get the last two terms. So because each sine function, by adding a positive or negative angle about same of 120 degrees, so those three atoms will be canceled. Finally, there are only 1, 2, 3 atoms here. So you can easily prove this formula. So anyway, so if we utilize this formula, that can be simplified to 3/2 of sine alpha minus beta. So we are going to use this formula to largely simplify the calculation of ID and IQ. First, we calculate ID. Okay, we just plug in those three into the orange expression, and we utilize this one to simplify, and we'll get this one. It's 3/2 multiplied by the amplitude, original amplitude, and here represent the difference of two angles. The difference of two angles, alpha here will be omega st. Okay, beta here will be theta, right? So omega st minus theta. So alpha minus beta. Next, we want to replace, we don't want to use theta. We may know delta. Delta represents the relative difference between the rotors, okay? But theta represents actual location. So we want to get rid of theta. We replace theta by this expression about the delta. So we'll have this second item. And we know the omega s is about same of omega r, so we can cancel the first two time-dependent terms. Finally, we get this one, which is constant. So if the delta doesn't change, this one doesn't change. So this proves ID is constant. It doesn't depend on theta or time. Further, we can do for the IQ, which is give you the same conclusion. So they are very similar. The ID will be proportional to cosine delta, and IQ will be proportional to sine delta. Okay, now we have at least two elements in this I prime. But think about the dimension of the current vector is 3. We have IA, IB, IC. So if it's under balance condition, if we know IA, IB, do we know IC? Yes, right? Yeah, under balance condition, IC will be 0 minus IA minus IB. But if it's not balance condition, we cannot do that. Okay, So we have to introduce something else, which is represent the sum of the three currents. But definitely in balanced condition, that sum will be 0. But here, let's just go ahead to define IAIBIC. We define this one, the summation, that may not be 0 under if the condition not steady state. We just go ahead to define the summation of those three currents as I0. So now we have three new elements. Those three currents are all direct current, DC current. So they don't change with voltage, don't change with the theta of time. Okay. Any question? All right, so we'll define this one to be the new current vector. This one can largely simplify the inductance matrix because we're going to replace the product of original L matrix, L block with the IABC by some L, maybe L prime multiplied by I0 dq. And there's no theta dependence. Okay, so now we can summarize or figure out what transformation we can utilize to obtain I0 dq from IABC. And which is through the transformation P. Okay, so from a previous slide, we know so ID will be those three atoms multiplied by IA, IB, IC respectively, and we calculate the sum that will give us ID. But actually, if here we just want to eliminate the dependence of the theta, you can also multiply a constant KD. You can take any non-zero value that will give you one ID which is not theta dependent. So you can scale up the ID or down by certain value. That doesn't change too much. You still can get rid of the theta dependency. Similarly, we can multiply any IQ by a constant value. Okay. So finally, on the I0, which is just simply the sum of the three current and multiplied by K0. So we introduce three constant value, non-zero constant values. So this one means the product of this, the first diagonal matrix and this second matrix, by taking any K value, that will give us a transformation. That transformation will get rid of the theta dependency. And this will be the general form of transformation. So you can take any value of K. So for balance condition, let's double check. Okay, let's just keep those K values undetermined. So ID will be this one. After transformation, so it will be only, is proportional to cosine delta. And IQ is proportional to sin delta. And I0 will be just simply 0. Okay, it's done. All constant. So under static condition, the ID, IQ, I0 all constant. Okay, next we need to determine the value for those Ks. Okay. So here we can add one very important condition. So we want to make this transformation be power invariant. Power invariant means it has preserved value for inner product. So before transformation, we can do any inner product, which means we do the dot product of a two vector. And what condition do we need to do dot product of two vectors when we calculate power? Because power is defined to be the somehow like a dot product of a voltage and current vector. If we use the voltage current in the original frame of ABC, we can calculate power. So now we apply the transformation to change to the frame of 0 dq. We also calculate power. We hope the two powers are equal, right? You don't want this transformation change the power. Originally, you operate the generator, which is 100 megawatt, but after transformation becomes 50 megawatt. You definitely want the transformation to be power invariant or inner product preserved. So in order to do that, we have to add another condition. So when we calculate the three-phase power, which is equal to the instantaneous power in the phase A, B, and C, which is equal to the inner product of voltage, three-phase voltage, and three-phase current. This is the inner product. And if we apply this transformation, that will be the inner product of the new voltage in the 0 dq and the new current. Okay, so which will give us this one. We hope those two are exactly equal. Then it doesn't change any power. So you can choose to use the transformation or not, but it never break any conservation of energy or power law. We just replace the original vector by the inverse of transformation multiplied by the new vector. That can be applied to both voltage and current vector. And we just do some simplification. We get this one. So the two items outside of those two expressions exactly identical. Okay, so we have to make this right one, the internal P, the inverse of P transpose multiplied by the inverse of P to be identity matrix. So this one the right one has to be identity matrix. So then we can meet this power invariant law. So we simply have this one. The final conclusion is PT transpose of P is inverse of P. So this type of matrix is called orthogonal matrix. So this is simply the definition of orthogonal matrix. So if one matrix, if you transpose it, the matrix, it becomes its inverse. So that's matrix called orthogonal matrix. Orthogonal matrix can preserve the value of inner product. So if you have two vector and the area between the two vector, after any such a orthogonal transformation, that area will be same. The area shape can change. It can become longer or become more narrow, but the total area will be same. So that preserves the inner product. Okay, then you just solve this one. So you have to take KD, KQ to be equal to the root of 3/3 and K0 to be 1 over the square root of 3. So you have to take that value to make the transformation to be orthogonal. Okay, this will be the final transformation and the inverse transformation. We call this transformation as parse transformation or 0 dq transformation. So the transformation itself is theta dependent. This theta dependency cancel the dependency of the theta with original flux linkage and current. And that will generate a new current, which is not depending on theta. Question? Everything clear? Okay, so if you find some other textbook which define QSs to be lagging D by 90 degrees, not leading, you will find out those two matrices will be changed. So the change will be on the negative sign in front of sign function. So those sign will become positive. Okay, but finally, when we finally derive the differential equation model is same, basically same. So don't worry about those negative signs. All right, so next we need to rederive this equation, the flux linkage equation in the new frame, in the 0 dq frame. So this equation is right now in the ABC frame. We know the LSS, LSR, LRS are all theta dependent. Only LR are not theta dependent. By introducing this transformation, the path transformation, we want to get the new equation which have no theta at all. So when we apply the transformation, the path transformation, we only need to apply to any quantities in ABC, not in 0 dq, which means when we apply the transformation to the entire current vector, only the top 3 elements are actually in ABC. with stator winding. But the last three atoms, capital F, capital D, capital Q, actually already in the rotor, 0 DQ, right? Because capital F, capital D are in D axis, capital Q in Q axis, it's in Q axis. So we only apply power transformation to the three currents in the stator winding, A, B, C, right? So for the IFDQ, we don't need to change anything. We just multiply that one by identity matrix. Okay, so next, for this equation, we multiply both sides by the inverse of this right one. So you will see this inverse matrix multiplied by the flux linkage vector in the new frame, which is equal to the flux linkage in the original frame, right? So that is just part of the original flux linkage equation. So next step, in order to derive the equation for the flux linkage in the new frame, both sides we multiply the inverse of this matrix. And also this one can be transformed, replaced by the new current in the 0 DQ frame. Okay, so next one, we just simplify this equation. We can get this one. So both sides is multiplied by the inverse of this matrix, which is just the PLI on the diagonal element. So this will be our new flux linkage equation. And next, we just simplify the product of the first three matrices. We just define that one as this new L matrix with prime. Prime just indicate after transformation. Okay, so here you will need to do a certain amount of work to really prove this equation to be true. I just tell the result. I will leave this one as a homework. Okay, after we finish maybe a third of this section, I will give you first homework. You have to redo the same procedure for round rotor generators. Okay. So round rotor generator has one additional winding, right? So ABC will be same, but this psi FDQ, you have to add another one. You call it Q2, or maybe use a different letter. This flux linkage vector or the current vector will become 7. We'll have 7 elements. And this matrix is also bigger. The matrix will not be 6 by 6, it will be 7 by 7. You have to do that in the first homework. But anyway, this will be the final result of the transformed flux connecting the transformed flux linkage and current. So there's no theta at all. Everything becomes constant. And if you tell the notations of each parameter, it makes a lot of sense. So this block indicates the coupling between the two stator winding. Okay, and it tells you after transformation, there's no coupling between two windings. There's only self-inductance with stator. Because A, B, C, they separate by 120 degrees. So their coupling is not 0. Phase A and then phase B, they separate by 120 degrees. So if you project to any coordinate, there will be two vectors, right, pointing to the different direction, which means they have some coupling. But when you change ABC to 0 DQ, the DQ is always orthogonal to each other. 0 is like another dimension, right? 0 is not, it's like orthogonal to DQ 0. So D and Q. So DQ 0 is like a new coordinate. Okay. And that get rid of the mutual inductances between those three stator windings. So we only have diagonal element L0, LD, and LQ. So we change all the L to capital because that's constant. We use lowercase to represent the variable. They just indicate the self-inductances. And this block, everything is M, right? Because this block represents the mutual inductances between stator winding and the rotor winding. Because these three elements multiply, those three elements, psi 0, D, and Q, multiplied by those values will give you the current in the rotor, right? So the top right block couples the stator flux linkage and the rotor current. And bottom left block couple the rotor flux linkage with the stator current. So everything in each block will be mutual industance. So mutual industance, we use capital M. So we use letter F, which means capital F just indicate this is mutual industance involve field winding. And capital D means this mutual industance involve damper winding D. And also there's a capital Q. Finally, in the last block, we have self inductances, which basically just coupling with for each individual rotor winding. Also, we have mutual inductances, and we only have MR, which is proved in the previous slides. And finally, earlier we have a lot of like a parameter like LS or MS in that slides with a lot of curves, but right now we simplify those one. We define some new value. Okay, so this one tell you the calculation of those new parameters. And there's also factor K. K that represents square root of 3/2. So this will be our starting point from here. All the future model will be based on this flux linkage equation. Okay, you're going to do the homework for the same procedure on the round rotor generator. Any question?
I know D is orthogonal to Q. Previous equation. Why zero is also orthogonal to D and Q.
0 is like a third dimension. That dimension is non-zero only when the three faces of ABC are not balanced. Yeah. Maybe it's not accurate to call it orthogonal. We can call D and Q to be orthogonal. 0 is just another dimension, whichever dimension. Just make up the original three-dimension space. Yeah. Yeah, if you want, you can define maybe I0 plus ID to be a new dimension. That's fine. That's also fine. But that you only have this physical meaning of I0. Want to make I0 to indicate the neutral current. So that's why we define I0. Okay, next we want to change this equation. This equation is about a voltage of each winding. So it will connect the vector of all winding voltages, all currents, and all flux linkages. Okay, so here we also define the new voltage vector in the reference frame 0 dq to be the vector transforming the original voltage vector by this path transformation. So which means if we know the new vector, we can have the original vector by using this inverse transformation. We just plug in this equation to the voltage equation we already know about A, B, C frame. Okay, so we'll have this equation. So for this equation, we do the same step by multiplying both sides by the inverse of this transformation. So which will be that will be PI will be multiplying the left-hand side on both sides. So the left-hand side equation will be the new vector, new voltage vector. So it will be something like this one. Okay, so we have a new voltage vector here, which is in the pink color, and we have a new current vector. And on the left, multiplying this current vector, we have three matrices, right? They together represent a matrix on all the resistances after the transformation. And the last item, which is the differential or derivative of flux linkages, that one need to be multiplied by the transformation matrix. And the vector of flux linkage also need to be replaced by the new flux linkage multiplied by inverse transformation. Okay. Is this clear? This last item is directly taken from the first one by multiplying the transformation. And this flux linkage vector is replaced by the new vector multiplied by the inverse transformation. So next, we just figure out what this one is and what that one is. We will get, it's done. We'll get the new voltage equation. We definitely don't want to see any theta in that equation. So if there's any theta, this mission is failed. Okay. Before we continue, we have to justify what this one is. This one really is just the transformation of the original flux linkage, derivative of flux linkage vector. Okay. Don't simply consider this one as transformed derivative of flux linkage vector. Why? Because when we prove P, we only assume P to be applied to voltage and current. If the flux linkage is proportional to current, it's fine. You also apply the transformation to flux linkage. But the transformation doesn't apply to this differential term. The differential term has the unit, which is 1/2, right? That one cannot be transformed. You cannot simply consider transforming the derivative of the flux linkage will necessarily give you a derivative in the new frame. That may not be true. We have to prove. If you can prove this one, that's fine. Then we can simply just reduce the last item to replaced by a simpler term. But we have to prove it. But unfortunately, it's not true. The reason is if you treat P as a constant matrix, by calculating derivative of a product of a two matrix, you can simply move the first constant matrix outside and will cancel with this one to become a dynamic matrix. Finally, only keep this one left, but actually P is not constant. Is this clear? Keep in mind, P is not constant. What is P? Yeah, it's a theta dependent, right? If it's theta dependent, it cannot be constant. So we cannot simply jump from here to that one. That's wrong. We have to figure out what this one is. So in order to calculate the derivative of the product of the two matrices, we have to utilize a formula, which is if we calculate derivative of product A and B, which is equal to A times derivative of B plus derivative A multiplied by B, right? So we have to use the same formula. We first need to calculate derivative of this one, multiplied by that. Then we add another term, which is the first one multiplied by second one, the differential of the second one. We have to just use that formula to do it. So this will be the final answer. So we'll have two items. The first item is simply just this one multiplied by derivative of the second one. And the first one will cancel with first one. The outside the transformation will have this item. But second item cannot be zero. So second item is some matrix transforming the new flux linkage vector. And if this one is theta dependent, so that will be a problem. So which means we cannot get the new voltage equation without theta. But fortunately, that one doesn't depend on theta. All right, so let's figure out how to calculate this one. So this one is simply equal to P multiplied by the first order derivative of a P inverse. Okay, we know P is theta dependent, which is equal to first calculate first order derivative with respect to theta, and multiplied by theta d theta dt. So this one is easier, right? P is like have sine, cosine, and theta. So you just go ahead to calculate this one. And d theta dt is omega r. It's a rotor speed. So this is constant. So if you consider like static condition, omega r doesn't change. So we move this one out as constant value. So next we want to figure out this one to be theta dependent or not. You just plug in the P and P inverse. So this is P. And this is the P inverse. And then we calculate the derivative with respect to theta. And that will make remember the first column of P inverse is constant, that becomes O0. And sine function become cosine function, and cosine function become negative sine function. So we'll have this one. And if you simplify this one, finally we have this simple matrix. We have only two elements, not zero. And both are not depending on theta. Okay. So finally, this whole bunch of things is basically just this matrix with almost all zero except for two elements, omega r and negative omega r. And the physical meaning of this one is very clear in the next few slides when we go back to the equivalent circuit of the generator. Okay, so good. So right now we just plug in this one back to this formula, and we have new voltage equation without theta. Because you're going to also use this one to multiply in the new flux linkage vector, so it will give you those three elements. The first one will be zero, because the first row of this matrix to be zero. Okay, so we go back, we continue to show the detailed voltage equation. So this is the flux linkage equation we had earlier, and this is the new voltage equation. We're going to figure out the value of each atom. And here we need to make assumption. We need to assume the resistance of each winding is same. So we can use resistance of winding A. So RA does indicate maybe the resistance in winding A or armature. So that is same to all the phases. Okay, then we have this equation. I ignore some steps. Similarly, what you need to do is on the paper, if you want to prove I didn't make mistake, you just plug in this one here, or maybe this one here. Okay, and RABC basically the diagonal matrix of RA. Okay, and let me see RFDQ. RFDQ is basically just diagonal matrix of RDIQ, because we don't know the resistance of the rotor winding. They can be made by different material. And the next thing, because this one introduced some flux linkage, I can borrow the flux linkage equation to plug into some of the atoms, just replace. We can just shape the derivative, time derivative to the current vector. So you'll have this one. So that omega r will appear here on those elements. Yeah. Sooner or later, after you finish homework 1, you will be very confident with those formulas. Okay. So from this step to that step, I just change the order of the row and the column and make 3 blocks. The first line is only in 0 direction, and the second block is only in the D axis. And third block, which is only in the Q axis. Okay, because the coupling between the 0 DQ can be ignored. So I can make sure after doing this one, and I have the inductance matrix, which is diagonal block matrix. Only we have non-zero block on the diagonal elements, right? All diagonal elements are all 0. So this is similar to memorize or use. Okay. Another thing I have to mention. So if you use this column or this row, the red row with the two red elements multiplied by the current, then you try to identify from those elements, you will know exactly that is about proportional to the flux linkage in Q. Similarly, if you use this blue row to multiply the current vector and identify those elements, that is exactly proportional to psi d. So which means we can somehow take those red and blue element out as the vector, additional vector, which is like input of the system. This will make the resistance matrix to be completely diagonal. And the inductance matrix can be block diagonal. And then the last column only have two non-zero elements. Each is proportional to a flux linkage. And the red element is shown in the d-axis at the first item, but which is proportional to flux linkage in q-axis. And the blue element is in the q-axis, but which is proportional to flux linkage in d-axis. So this make a lot of sense if you go to the actual circuit. Okay. Before I show the new equipment circuit, I have to quickly address how to deal with the unbalanced condition. So early we treat the three phases to be balanced, which means if under balanced condition, the neutral point will have voltage of 0, and the current will be 0. There's no current, but if those three phases not balanced, there will be a current going to the ground, like short circuit current, if you have unbalanced conditions. This can happen in reality, because in real situations, usually most of continuously are not balanced, they're unbalanced. So under fault conditions, so the neutral point will have non-zero voltage with non-zero current to the ground. So I have to figure out how to model this non-zero current or voltage. So we just add the last item to the voltage equation. So which is transform, because everything in this equation already transformed by P. So this P also need to transform the neutral voltage. So we need to figure out what this one is. Okay, so if we study fault condition, we will add this vector. Otherwise, we just get rid of this vector. What is this? This item is, so the neutral voltage, although I tell it like EN, which is a neutral voltage, but actually for three phases, they can be treated as independent three phases. They just simply separate by 120 degrees. Okay, so you can replace this point by three separate points. So which means you are going to see that voltage in all the A, B, C phases. So this is phase A, phase B, phase C. Then you use that neutral circuit to each of the three phases. So you will have this equation. This basically just three-phase voltage equation applied to neutral point. If you separate that neutral point to separate the three phases to three individual circuits. So this is how to calculate the EA. What is a PE, PEM? PEM is just transform the neutral voltage. So you use P multiplying this formula, and you also, okay. By changing the current from ABC to the 0 DQ, you're going to have this matrix represent the transform the neutral resistance and transform the neutral inductance. You just calculate what it is. Okay, in the first transform, the resistance will represented by matrix only have non-zero element in the first element, and the inductance matrix only has one non-zero element. So next, you just plug in those back to the equation, you'll get this one. Okay, this one tell after transformation, the neutral voltage will be equal to the first line of this equation. And the other item is 0. So this is the only thing we need to add. So we just add this one to the voltage equation. We only just replace the first item corresponding to the neutral voltage by this one. Okay. Definitely, if I0 is 0, if there's no fault current, I0 becomes 0, the first item is also 0. That will go back to the balance condition. All right, just summarize what we learned so far. Okay, so we assume there's a transformation. We can change the original current vector to a new current vector in 0 DQ, and we prove that transformation has to be this one, to be power invariant, to preserve the inner product value. And we use this one to transform original flux linkage equation, voltage equation, to new flux linkage equation and voltage equation. And this voltage equation will also consider the neutral voltage and neutral current under unbalanced condition. That's what we have done so far at this lecture. This table, just for your convenience to understand the Quinter's book, because Quinter's book is using a totally different system, but I try to give you this table so you can easily understand so what each notation means in my slides. So in my slides, I use capital letter to indicate around any quantities with rotor, right? So we have F, capital F just means field winding, capital D means damper winding D, capital Q is damper winding Q. I use S means self. I use M means I use L means self inductance. M means mutual, and this subscript S means stator. Okay, and later capital M just indicate mutual inductance. So the capital F DQ just indicate which one is coupled. Okay, but in Quinter's book, so for current, the field winding current, you just use FD. FD just stands for field winding. And KD, because Quinter book allow considering many different damper winding D. So K may be a number. So if you see you see I1D means first damper winding. The current in the first damper winding. You see I2D, which means current in the second damper winding. Similarly, if you see I1Q, which means the current in the first damper winding Q. So if you try to find the capital MS, which is LAB0, because Quinter book proved this one based on the constant part of the mutual inductance between A and B. They use that one as an example to explain the mutual inductance. So that's why they call it this one. They keep using this notation. Okay. When the book try to figure out the LM, which represent the constant part of the self inductance between two same stator winding, they use A winding as an example. Okay, and they put 2 because that is related to second order harmonic. Okay, if you don't want to figure out the naming convention with Quinter's book, just use this table. So later one, you see this is like mutual inductance between stator winding and field winding. It just use A, FD. A is from stator and FD from field winding. Okay. I need to, I think I need to finish this slide so to finish. Okay. I need to explain what this red item or the blue item really mean in the physical world. So if we forget everything we have considered about generator, we just try to derive equivalent circuits only based on this equation. So this will be the final result. Because those voltage equations separated into 3 groups, 0, D, and Q. That means there's a 3 set of circuits. There's a circuit in 0 axis and D axis and Q axis. So for the 0 axis, if you pick the first equation, first row, that's basically talking about this simple equation. So there's a neutral voltage added to the stator winding with stator resistance, and there's a neutral inductance. Okay, so if a balance condition, this neutral voltage is 0, this current is 0. That simply is about the first circuit. Okay, the second group, it involves 3 windings. There's 1 stator and 2 from a rotor. So that will involve 2 rotor winding and 1 stator winding, D. So this is like a 3 winding transformer. They have 3 winding coupled through those mutual inductances. And the last group involves 2 windings, 1 from stator in Q and 1 damper in rotor in Q. So that is coupling between 2 windings, which is like transformer, 2 winding transformer. Okay, so the only thing is different from transformer here. If finally we prove generator is simply that transformer, that's ridiculous, right? Transformer, how can generator be transformer? Because we have those 2 items. Those 2 items make a generator not be a transformer. And if you check out those 2 items, so this one is like a source, right? Because we treat this one as input. Don't worry about negative sign, but you just, because think about those can be some value, changing value. Those just the input. Okay. So the input to the D axis is something proportional to the flux linkage in Q. And that coefficient is speed. And the input to the Q axis is proportional to flux linkage in D and also proportional to speed. So what does that mean? That means the generator will have a source which is proportional to speed. So which means when the speed changes, the generator, the voltage also changes. And the flux linkage in Q will influence the voltage seen from D, and flux linkage in D will affect the voltage in Q. Okay, so we call this omega R psi D as a speed voltage because it's proportional to speed caused by D axis flux in the Q axis winding. And similarly, this item is speed voltage caused by Q axis flux in the D axis winding. If I show this equation, it will be very clear why we have that item. This is Faraday's law. It tells any voltage due to the electromagnetic field, this one will be contributed by 2 parts. One is delivered through electric field, the other delivered through magnetic field. For the electric field, if you only have this part without speed, which that is exactly a transformer. So if I have a generator not revolving at all, the speed is 0, which is like you have generator. So that generator will be just transformer. So what is the source of the generator now? Basically this one, right? That's the only source. And those 2 are 0, right? So you are using the field winding as a source to input some electricity, and at the terminal you will receive some electricity. That one can be ignored because the field winding is not the major source of generator. That only just generates the magnetic field. So the really electric source really caused by the revolution of the rotor. You have to make this speed to be high enough to induce the electric field due to this one. And here is a cross product. So V is like omega, right? B is like a flux linkage D and Q. The cross product is plain Y. The Q axis flux will influence the D voltage and D influence Q voltage. If you treat the psi D, psi Q as 2 elements of some magnetic field in orthogonal coordinate, you can easily use this one to prove the sign, okay, in front of those 2 items. Okay, so this is my last slide. So this tells you eventually when we generate the first detailed model, and those will tell us the major source of the voltage, the power. Okay, so you can somehow simplify some winding which doesn't contribute to the source or the voltage, but you have to keep those 2 items always with your model. Yeah. it should be electric speed. Yeah, but if we treat all the generator just have with 2 poles, that's same, that basically same. We don't bother about don't bother with figuring out what the mechanical speed is because we don't know how many poles they have. We don't have to. Yeah. Okay. What else I need to see? All right. So the last thing I need to mention, is this a good model? If you check our 2 criteria, first of all, there's no time-dependent value, right? They're all good, all constant value, which means this is my equivalent circuit. If I have any way I can identify all the parameter, I'm safe to carry this parameter to somebody else. They can use those circuit, but it still involves a lot of parameter, right? So in the next part, we'll try to figure out whether we can further simplify the circuit. But for instance, this is like the transformer, but even in transformer, we can have equivalent circuit. You can have same circuit connecting directly of both winding, but right now you have to draw the winding separately in different circuit. We want to have maybe 1 or 2 circuit representing the entire generator. All right, okay.